Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics. This lecture is entitled Designing Synchronous Counters. Okay, so in our previous lectures, I have been giving you synchronous counters and we've been just performing an analysis of them. And the question remains is how do you actually make one of these things? So I mentioned previously, it's kind of an art form. And what I'm intending this lecture to be is art school. I'm going to give you a systematic method to go ahead and design a synchronous counter. And we are going to be using JK flip-flops. You can do the same thing with D flip-flops. Takes a little bit more logic, but we're going to go ahead and use JK flip-flops for these purposes. When we created a 2-bit binary up counter, it was kind of one of those things where we can see the transition. In a state diagram for a 2-bit binary up counter, let's say we're in state 0, 0, we're going to count up. We're going to go to 1, 2, 3, back to 0, and so forth. We can see that. And we can visualize, when do I want that MSB to change? Well, it will toggle when the LSB is 1. Okay, if you think about this, you can kind of see this. Okay, when do I want this to toggle? When its previous state was high. When do I want this to toggle? Like here it's 1. It's going to toggle to a 0 when its previous state was high. We can see that. When do we want the LSB to toggle? Well, all the time, because I can see that. It's was a 0, going to a 1, was a 1, going to a 0, 0, 1, 1, 0. We can see that. Not so easy all the time. In our first example of this, what we're going to do is design 2-bit gray code up counter. First off, start off with a state diagram. What does a 2-bit gray code up counter state diagram look like? Chances are it looks something like this. We are in state 0, 0, go to 0, 1. We are in 0, 1, go to 1, 1. Notice only 1-bit position changes at a time. That's the advantage of gray code. And then let's count up, go to 1, 0, count up, we recycled back to 0, 0. And we can do that same thing with the truth table. Present state 0, 0, go to 0, 1, 0, 1, go to 1, 1. And notice here I'm purposely not counting in gray code for the present. I'm exhausting all binary combinations. So now what I'm doing, I'm in 1, 0. Where do I go? I go to 0, 0. I'm in 1, 1. Where do I go? 1, 0. So again, keep the order for the present state in an exhaustive binary combination. And what I've kind of drawn here is it's a synchronous counter that has a clock tied to it. It's 2 stages, obviously, because it's a 2-bit counter. But what is the logic that we want to put on those J and K inputs? And quite like our last example in an analysis of synchronous counters, those J's and K's don't have to be tied together. We're going to get independent logical values for them. How we do this is a very systematic means. What we have to do is basically start with an analysis of how a JK flip-flop works. If the present state is a 0 and the next state is transitioning to a 0, i.e. it's staying the same, what could we have on our inputs for J and K? Well, put it in memory state, 0, 0. Okay, if it's memory, we're going to be good. However, what if I was to reset it? Well, if it's already a 0, resetting it doesn't change it also. So I could also potentially reset it. So it sounds like that K input doesn't matter. Doesn't matter. It's going to be an X. All right, let's look at that next stage. If the present state of that input is a 0 and at the next clock pulse it transitions to a 1, what do I want to do? Well, maybe I want to set it. How do I set something? 1, 0. Well, if a 0 transitions to a 1, I could also toggle it. So how do I toggle something? I'm actually going to go ahead and put a 1 on the K input. So it sounds like that, again, that K input doesn't matter. Now, let's go ahead and consider our third case. If we are a 1 and we transition to a 0, well, maybe I want to reset it. Well, also, what about toggling it? What if I toggled it? That would also make it go to a 0. So I could also potentially toggle the thing. So it sounds like the J input doesn't matter. Now let's take that final consideration, 1 going to a 1. Yep, that's a memory state. Definitely memory. Is that the only thing that could happen? No. What if I also set something that was already set? I.e. put a 1 on the J. Sounds like the J input doesn't matter. So what we've created here is a truth table that we can use when we perform the analysis of this. That's exactly what I'm going to do. I know, in this case, for designing synchronous counters, I know the state machine diagram. Or from the requirements of the device, I'm capable of figuring out the state machine diagram. So I've got the present state and the next state. What I have to do is figure out the logic for the J and K flip-flops. Whereas previously we had the analysis of synchronous counters. The analysis of synchronous counters, we knew the present state, we knew the logic for the J and K flip-flops, we tried to figure out the next state. So designing a synchronous counters, we've got that overarching general description of how we want the thing to behave. What we're doing is we are actually going to come up with the logic for the J and K flip-flops. This is how you do it. You have the present state. You have the next state. Where do we get that from? We got it from the state diagram. Put them right next to each other. How many stages do you have? Well, this is a Moore machine. Its next state is dependent only on its present state. So there's no external input for this thing. Anytime there's a clock pulse on this thing, it's going to count in gray code. I've got inputs for the Q1 stage, and I've got inputs for the Q0 stage. And this is where it helps to have like kind of those colored markers. This is Q1's present state. It is transitioning into Q1's next state, where its inputs, it's these guys. And do the same thing for Q0. Okay, let's just stick at Q1 right now. Just divide these things up into their own separate realms. Okay, look at Q1's present state. It's presently a 0. It's going to a 0. Where are we on the truth table? We're right there. J could be a 0. K could be don't care. Okay, move on to the next one. Q1 is presently a 0. It's moving to a 0. It's moving to a 1. Where are we? We're right here in our truth table. So J could be 1. K could be don't care. Now move on to the third one. We are a 1. We're moving to a 0. Where are we? Right here. Okay, so J could be don't care. K could be a 1. Finally, we are in a position where Q1 is a 1 in its next state for a 2-bit up gray code counter. It stays a 1. So where are we on the truth table? 1 is transitioning to a 1. J, don't care. K, 0. What do we do with this stuff? Don't worry about it right now because we're only half done for the truth table. We got to go ahead and figure out for Q0. Okay, so this is what I'm saying about using color codes or somehow organizing it. Forget about Q1. Let's look at Q0. Q0's present state is here. It's transitioning to its next state on the positive clock edges. What are its stages inputs? They're right there. Look at it. Was a 0. It's transitioning to a 1 right there. 1x. It was a 1, staying a 1. Where are we? Don't care. 0. Next one, 0 moving to a 0 right here on our truth table. 0x, not truth table, a little cheat sheet. Finally, we are a 1 going to a 0. Should be don't care 1. So now what am I going to do with all these J1, K1, J0, K0 inputs? Well, what I'm going to do is just try to figure out the minimum SOP expression for J1, the minimum SOP expression for K1, minimum SOP for J0, minimum SOP for K0. How do I do that? Use the Carnot map. So what I've got is 4 pre-made Carnot maps here, and what I've got is Q1 on the left, Q0 on the right. Again, we've got 2-bit input here. If we had some external input, we'd have to go ahead and account for that, but in this case, it's a Moore machine. Its next state is its next state is only dependent on its present state. All you do is just take J1, put it in the its appropriate K-map, come up with its minimum SOP expression, do the same thing for K1, do the same thing for J0, do the same thing for K0. So let's go ahead and just take the J1 column, go ahead and put it in the K-map. I see 0, 1, don't care, don't care. What is the best expression you can come up with for J1? Okay, what I see is right there. That's my best group. Yes, I could have just grouped that upper 1 in the upper right hand corner. However, if I'm making use of the don't cares, if they help me, I'm not making use of them if they don't. For example, I would not include this lower group of 2 because I've already accounted for that. Okay, what is that? To me, J1's expression looks like it is Q0. So do the same thing for K1. What does K1's populated K-map look like? It looks like don't care, 1, 0. Go ahead and find its group. Let's look at like that. So to me, K1's expression should be not Q0. Now go ahead and populate the K-map for J0. What we've got here is 1, don't care, 0, don't care. What is its expression? I'm finding that to be the best group. What is that represent in the K-map? Looks like that minimum SOP expression is not Q1. Okay, we've come up with a minimum SOP expression for J0. Let's move on to K0. Take the K0 column, populate the K-map, don't care, 0, don't care, 1. Go ahead and come up with a best grouping for that. What I find is right here, this group of 2. Again, I'm making use of those don't care situations if they help me. I'm not making use of them if they don't. That expression there is Q1. In a perfect world, what we've come up with here is the expressions for the individual J's and K's that will set, reset, or stay that particular stage at those positive clock edges to go ahead and initiate a 2-bit gray code up counter. The last step for all this thing, the last step, check your work. Go ahead and do an analysis of synchronous counters. Implement the device, do the analysis of synchronous counters, and see if this thing really does count up in gray code. So let's go ahead and set it up for that. So what we've gone up here is went ahead and implemented that device. So we put that logic on those J and Ks for the respective stages. And again, J1 has Q0, K1 has not Q0, and J0 has not Q1, K0 has Q1. These are the resultant logic that we came up with our designing portion of it. We're going to go ahead and check to see if this thing works. How do we do an analysis of synchronous counters? What we do is we just come up with a J and K expressions for each stage, evaluate those inputs based upon our present combination of inputs, and then figure out the actions for those respective stages. Okay, so what is J1, K1 values and actions given present state 0, 0? Well, J1 is always Q0. So I can go ahead and just fill out that column. What's K1? What's not Q0? So I can just say 1, 0, 1, 0. Our action, what is the action based off J1, K1, 0, 1? It's reset, set, reset, set. Go ahead and look at the expressions for J0 and K0. J0 is not Q1, so I can just say 1, 1, 0, 0. K0 is Q1. So what it's going to do is going to say 0, 0, 1, 1. What is the action based off those inputs? That is a set, a reset, a reset. Now what we're going to do is go ahead and use those actions for those respective columns and go ahead and figure out our next state. And if everything works out correctly, you know what it should do? It should do this. That is our 2-bit gray code up counter. So what we're going to do is just checking our work. Did our logic work? So this section here deals with the transition of this present state to this next state. Okay, go ahead and do that analysis. If it is a 0, it's being reset to a 0. If it is a 0, it's being set to a 1. If it is a 1, it's being reset to a 0. If it is a 1, it's being set to a 1. Go ahead, do that same analysis for the Q0 inputs. Where are the Q0 inputs? Right there. That action is affecting this present state, and it's changing it to that next state. So if it was a 0, it's being set to a 1. It was a 1, it's being set to a 1. If it was a 0, it's being reset to a 0. If it was a 1, it's being reset to a 0. Go ahead. Does our resultant finite state machine do what it's supposed to? Okay, our design implements 0, 0, it goes to 0, 1, looking good. It is 0, 1, it goes to 1, 1, looking good. It is 1, 0, it's going to 0, 0. That's that transition right there. We're looking good. Finally, our last state, 1, 1, where does it go to next? 1, 0. Oh my gosh, our design worked. So systematic, again, systematic, that's the way you go ahead and do that. Take that present state, compare it to the next, and use that cheat sheet right here. You have to know how these things work given a present state and you know its next state. Go ahead and figure out what those J and K inputs. Again, just take those individual J and K inputs and put them into their own individual K-maps and come up with a minimum SOP expressions for it. So that was a Moore machine example. Again, what is a Moore machine? Its next state is only dependent on its present state. What if I had an external input that I wanted to go ahead and have different modes for my finite state machine? So let's go ahead and do an example of designing a synchronous counter that is a Mealy machine, which next state is dependent not only on its present state, but also some external input. Okay, so our second example of designing synchronous counters using JK flip-flops is a pretty neat example. It's a finite state machine with external inputs. And the astute among you may realize that this state diagram, which I've drawn right here, is the exact same one for the example that ended the analysis of synchronous counters. So ideally what's going to happen here is when we design this, we should get a fully minimized SOP expressions for those J and K inputs for each stage, which exactly matches the analysis of synchronous counters example. Again, look at the state diagram here. What it represents is a 0, 0 start state when X is 0. it goes to 1, 1. So it's an external input. When x is 1, it goes to 0, 1. So there's two choices. There's a single choice, but there are two exits. You either go x is 0, 1, and you're going to go two different directions. If it's 0, it's going to keep on going in this direction and keep on going in that direction. The 0, 0 is just a feed-in state. Whereas if it was in 1, if x was 1, we were in 0, 1, 1, 0, 1, 1, back to 0, 1. If at any time, however, we switch modes, let's say, for example, we are in state 0, 1, we are in mode 1, we would go to 2, but if the mode suddenly switches to x equals 0, where would we go? We'd go back to 1. So using the state machine diagram, let's go ahead and figure out what our present state of inputs are. And when I say inputs, again, it's present state and the external input. So there's how many inputs here? So there's two stages for the present states, Q1 and Q0, and an external input. So there's 3 inputs. How many possible combinations? It sounds like there's 8 possible combinations for this. And then just go ahead, based off those present states and external inputs there, go ahead and figure out what the next state is. So what I've drawn here is a bare truth table. I'm kind of setting you guys up for this already. And this is kind of what I'm expecting you guys to have an understanding of this is just this is systematic. Again, this is art school. I'm giving you the steps to go ahead and do this. What do we do every single time? Just look at the state diagram. Here's our inputs. We are in present state 0, 0. We are in mode 0. What's our next state? It sounds to me like we'd be moving to 1, 1. Okay, we are in present state 0, 1. Our mode is 0. X is 0. Where do we go to? Its next state is also 1, 1. Again, how am I doing this? I'm just looking from the state diagram. Our first one, we went from 0, 0 to 1, 1. Now we are in 0, 1. We're going to 1, 1. Let's go ahead and if you can see if you can figure out the next state, i.e. the output for based off that state diagram. See if you can go ahead and figure out the next Q1 and Q0 state. So hopefully your next state outputs look the same as mine. And again, let's just pick an example here. Okay, we are currently in present state 1, 0. However, we are in mode 1. Where are we? We're right there. We're in mode 1. Where do we go to? 1, 1. Okay, so just reading that state diagram and putting it into this table. All right, now what do? We divide these things up to each stage's inputs. J1, K1, it is looking at that one's present state and it's transitioning to this next state. So it was a 0, it goes to a 1. Where are we? Right there. So what we do is just fill out these columns. 1, don't care. Finally, this next one here, what is it? We are in a 0. We're going to a 1, so we're in the same spot. 1, don't care. And let's go ahead and see if you can compare each one of those present states of Q1s and the next states of Q1s and use this truth table, the little cheat sheet truth table there, to go ahead and figure out for the J and K inputs. And hopefully yours should look like this. Okay, so those are J1, K1 values. Now just go ahead and again, what are we going to do now is look at Q0's present state. It's transition into Q0's next state. What does it affect? What are its inputs? Excuse me. It's J0, K0. So it's presently in 0, moving to a 1. Where are we? It's 1. Don't care. Now we are in 1, moving to a 1. Where are we? Don't care, 0. Go ahead and see if you can fill out the rest of the J0, K0 column. And there we go. Hopefully the J0 and K0s look very similar. Now what's our next step? We're going to go ahead and put J1 into a K-map and develop the minimum SOP logic expression for it. Do the same thing for K1, do the same thing for J0, do the same thing for K0. And the key thing is just only do the expression for J1. Don't try to combine J1 with J0 or K1 and K0. So it's entirely separate. So let's just look at J1. Let's just go ahead and try to fill out the K-map for J1. And again, if you need help with K-maps, just go back and some of the K-map lectures. Should be pretty familiar to you. So it's 1, 1, don't care, 0, 1. Notice the gray code there. Don't care, don't care. How do I develop the SOP expression for J1? Again, groups of 1, 2, 4, 8, 16, 32, so on and so forth. Use the don't cares if they help you. Don't use them if they don't. So here's my first group right there. It's a group 4. That looks like that is Q0. My second group, I'm going to grab a group of 4 also. What is that? That looks like not X. So my final SOP expression for J1 is Q0 or not external. Okay, and if you remember right from our previous example of analysis synchronous counters, that's the original input I gave. So we're tracking here. Go ahead and see if you can populate K1 map, populate J0 map, and populate the K0 map. Just do the population right now. So hopefully we're starting off at the same spot. So there is the population of those individual K maps, and let's look at K1's expression. So come up with a minimum SOP expression for K1. What I'm going to go ahead and do is I'm going to grab this group of 2 right there, and I'm going to grab this group of 2 right there. Okay, so the group in blue, what is that? That is not X and not Q0. What's the group in red? The group in red is Q0 and X. Okay, so the final SOP expression for K1 is not X and not Q0, or Q0 and X. Okay, J0's expression. J0's expression is pretty neat here. Look at it. Okay, we've got a column of 1s all the way down in the not Q0 column. But look at, we've also got X's, i.e. don't cares, in that Q0 column. So what would you do? If it doesn't matter if it's a 0 or 1 for the Q0 column, just go ahead and group the whole thing. Okay, it's a group of 8. What is a group of 8? Basically, it's always going to be a 1. Okay, so J0 is always going to be a 1. Let's go ahead and look at K0. What I'm going to do is find a group of 2 right there, another group of 2 there. What do I get here? So this first one is going to be not X and Q1, or X and not Q1. Excuse me. X and not Q1. So now what we can do is take the final SOP expressions for those J1, K1, J0, K0 inputs for each stage and go ahead and implement it. And what we came up here with is exactly what we had originally had in the end example of the analysis of synchronous counters. We figured out the state machine diagram for this one actually does implement with what we've designed here. So again, I can always go back and check my work using what I developed for the J0, K0, J1, K1 stages, and go ahead and see how this works using that tabular method for analysis of synchronous counters. So let's go ahead and close up this lecture with a couple things that you might be able to tackle here. Just here's some suggested exercise. And I'm not going to give you the state diagram for these things. Whereas previously I had given you guys the state diagram, I'm going to go ahead and have you design it from there. I'm actually just going to give you guys a verbal description of these things. And so that's one of those steps here. You got to take this leaps of logic. What does the state diagram for these 2 suggested exercises look for? So for the first one here, think about a 2-bit binary or gray code up counter. So it's got an external mode. Okay, that's called B. Let's call it B slash not G. Okay, so that's an external input. When that B slash not G is 1, it's counting in binary. When B slash not G is in 0, it's counting up in 2-bit gray code. So there is an external input in addition to its present state. How would it look in the state diagram? And let's say it switches mode. Okay, so it was in binary mode and it is in a certain present state and it suddenly switches to gray mode. Where would it go? Obviously go to its next gray code sequence based on that present input. So this is pretty neat, these conceptual exercises to actually visualize how these things work in a state machine diagram before you even do any of these techniques that we've done in this lecture here. The next suggested exercise, this is a good one here. See if you can design a 3-bit odd even up counter. So we've got 1 input, odd slash even. So let's go ahead and say it's an external input. There's that external input that's making a decision where it goes. So let's go ahead and say when it's in 0, go to even mode. When it's in 1, go to odd mode. And by the way, too, you don't have to use this clunky notation for these external inputs. You can call it X or EX or E or whatever you want to do. Actually, don't call it E for that particular exercise. Just come up with something memorable. You don't have to use those clunky notations. But think about this 3-bit odd even up counter. If it's in odd mode, it's going to obviously go to the next odd number, highest in the sequence. So for example, 1 goes to 3, goes to 5, and so on. If it's in even mode, it's going to go from 2 to 4 to 6 and so on. But what happens if it's in even mode and an even number, let's say 4, and it suddenly switches to odd mode prior to the next clock sequence getting that clock edge? What would it do? Well, it would go up to the next odd number. So see if you can come up with the state machine diagrams for these things. These are excellent exercises. Practice what we've learned in this lecture here, designing synchronous counters using JK flip-flops. Okay, let's go ahead and see if we can, in our next series of lectures here, go ahead and describe some counters using some different technology.